Well, Brady, I thought today we'd discuss where do the particles come from in the universe. There's a period that went on in the very early universe, which we've discussed before, which solves lots of problems, but it leaves us with one little problem. It's emptied the universe of all the particles. But here we are, right? This beautiful sunny day. We've got particles all around us. We've got radiation. We've got matter that's clumped into galaxies. We know what the standard model of physics is, and all these particles are there, but they weren't there at the end of this period, which we needed early on. So I thought I would try and just spend a few minutes explaining where we think these particles have come from.
All right, so where does the story start?
We live in the universe which we christen the Hot Big Bang. And the Hot Big Bang, we had some particles that are expanding out because the universe is expanding. And when we look at the universe, it's very flat. It looks like if you're on the surface of the Earth, when you look across it, you barely see any evidence of curvature. It looks really flat. And our universe might be slightly curved, but it looks beautifully flat.
What do you mean by flat? Because the universe is three-dimensional. Like, what do you mean by the universe is flat?
So there are these ways of talking about the spatial curvature of the universe. Yeah, indeed. We could be living on a sphere. The spatial curvature of that in terms of the overall space-time is spatially flat. That's got a positive curvature. There's a thing with a negative curvature, which is the universe spatially would look like a saddle that you put on a horse, that sort of can curve up. That's got a negative curvature. The universe could have a slightly negative curvature, slightly positive curvature, or it could be the spatial sections themselves are flat. We think that they're consistent with being flat. At the same time, when we look out at the sky and we look at the radiation that comes to us from the cosmic microwave background that was emitted about 300,000 years after the universe began, the radiation is the same in all directions. It's got the same temperature. It looks exactly the same in all directions. When we look on really large scales in the universe looks what we call homogeneous. That we're clearly not homogeneous. You and I, although we're both incredibly fit and we do lots of exercise, we don't look the same. The planets don't look the same, the stars don't look the same. But if you go to large enough scales, then on average, the distribution of matter looks the same. That's called homogeneity. We're in no special place. And then finally, there are no obvious, huge, what we call topological defects, monopoles in the universe. These are objects which, if they were around, would have caused the universe to have collapsed because of their abundance and their mass. And they're not there. This is the universe we live in. But all of those aspects, the fact that the universe is beautifully flat, the fact that it's so isotropic, the fact that it looks homogeneous, the fact that there are none of these what we call topological defects present, these are all an issue. They all have to be fine-tuned in the standard Hot Big Bang in order for us to explain why they are what they are today, because the universe is 13.7 billion years old. And for example, the flatness, if you had a little bit of curvature in the universe and you evolved it for 13.7 billion years, it would become really curved. And we don't see it. We see it flat. So it must have been incredibly close to being flat early on. So this is what then led to the idea of inflation. Inflation came before what we would call the Hot Big Bang. And inflation was this idea that if you had a small enough patch of the universe where everything was causally connected, so light could have interacted with all the regions of it, and then for some reason or other, it grew exponentially rapidly for a very short period of time, but it grew by a factor of about 1 billion times, 10 to the 27 times, so some huge region, over the time scale of, I think it's a millionth of a millionth of a millionth of a millionth of a second, then that would be enough to have caused the universe to be incredibly close to being flat, isotropic, so it looks the same in all directions, and it would crucially have given you one extra ingredient. It would have given you the small fluctuations, which then would have led to galaxies forming. So that's probably the biggest thing from inflation.
But that's before the Big Bang.
Yes.
But it's already banged.
No. Something else happened to lead to inflation, which we don't know. So that's where a lot of research is in trying what led to this period of inflation.
What's that called, the thing that triggered inflation?
Well, some people would call it sort of the initial singularity, what happened sort of that then led to the universe to emerge in the first place. But what we tend to call the Hot Big Bang, where the universe is full of radiation, that has to come at the end of this period of inflation. If you're not happy to accept these initial conditions of the Hot Big Bang and you want to explain them, you want something that can explain them, And that's why inflation was there.
So when the Big Bang happened, I know that we're not talking about the Big Bang, but when the Big Bang happened, the universe was already had quite some size to it.
The region that actually would turn up to be our universe wasn't that big, but it was of order of, sometimes people talk about it being like the size of a melon or the size of a basketball or something.
That billion and million stuff you were blowing my mind with.
Yeah.
Because the start was so small, it's still not very big.
Yeah. In fact, the region that we require was incredibly small, that then hadn't grown to such a big scale for our universe that we live in. But the actual whole region that was affected grew much, much bigger. And so that could be ginormous. And we haven't experienced that bit yet. We're evolving, gradually encompassing more and more of it.
We've currently inflated and we're like a melon.
So the universe it's created these small fluctuations as well, which has then led to the structures that we see much later on. And so one thing that drives inflation, I should just mention, is we have these things called scalar fields. We're all beginning now to hear about scalar fields. We've heard about the Higgs field, right? These are fields, are mathematical quantities which fill space and time, and their vibrations are what lead to particles. So when particles are created, there's lots and lots of vibrations of the scalar field. The Higgs field is the most famous one, but each particle has its own field associated with it. So there was one that's postulated called the scalar field for inflation, called the inflaton field. The energy stored in that inflaton field is what drove this acceleration. Okay, so where's the problem? Here's the problem. Any particles that were around before inflation started, inflation drives this acceleration so rapidly that the particles just get diluted away. Any curvature that was present gets stretched. Imagine you have a rubber sheet and you pull it rapidly, and then all the fluctuations that rubber sheet just get flattened out. It becomes effectively flat. And the particles that were in there, they all just get pushed to the side. So we end up with a universe which is very big, but it's very cold. The temperature of any radiation that's present goes as 1 over the size of the universe. And that size has grown by, what did I say, 1 billion times. So the temperature of any radiation has effectively dropped to 0. All the particles have gone. So we've ended up in a universe, which is going to be our universe, which has got no particles, effectively no radiation because it's all at almost 0 temperature, is empty, and there's no structures there. Welcome to our world.
Nice.
So I've got to reheat. This is called the process that I'm going to describe as reheating. And we're here at the board because, as it happens, it's an area of active research, and so I've got some project students working on this, and then I'm doing some work with a postdoc here, Swagat Mishra, who did a video as well, and with some of his colleagues from India. But I just have this little diagram here. This is, in funny units, it's like the size of the universe. It's sort of 1 over it. So it shrinks rapidly during this period here, which we call inflation. Okay?
Shrinking? I thought it expands in inflation.
1 over the size. 1 over the size. So,
of course.
Yeah. Then why use those units? So this is shrinking, and then the standard hot Big Bang, which is expanding, is this bit over here.
So that's shrinking. You're 1 over, so that's shrinking at that point then.
Right, so these are called, okay, it's a bit more subtle. These are called co-moving coordinates. During inflation, this parameter h is a constant. This is the Hubble parameter. It's here. This is effectively the size of the universe, a, the scale factor. The Hubble parameter is the derivative, a dot over a. God, you're letting me do some maths in a 60 simples video, I don't believe it. So it goes as 1 over t. So during radiation and matter, this decreases.
During radiation?
Radiation domination, a universe that's full of radiation. And in fact, this is the solution when it's full of matter. It goes as t to the 2/3. So h decreases. So 1 over h is here. So that goes as t from the 1 over h. A is going as t to the 2/3. So this grows. This quantity, which I'm plotting, grows in that period.
So even though that line goes down and then up,
Yeah.
even though that line goes down and then up,
Yeah.
it's always getting bigger.
So, yeah, the size is getting bigger. It's just the rate at which the size gets bigger is important here. So this is this. Friedman Roberts.
Oh, so that line represents a rate, not a size.
Well, it's effective. Yeah, it's a rate, really. Yes.
Yeah.
I mean, if I think of A as not having any dimension, this is effectively a rate. Yeah.
Okay.
It's been put. So we have the inflationary bit here. We have the standard universe that we're living in here. It's coming down a bit here because of dark energy. Dark energy is causing the universe to accelerate again today. We've done videos on dark energy. But there's this bit here which connects the end of the inflation to the start of the hot Big Bang. And that's the bit we're now just going to talk about. That's the reheating. That's where we've left this bit here. As we've left inflation, the universe is flat. It's got no monopoles. We've got fluctuations that have been created. It's isotropic. It's fantastic initial conditions, but there's no particles. So now we've got to create the particles.
Big Bang still hasn't happened.
Big Bang hasn't happened really yet. For me, the Big Bang is going to be when we've created those particles and then the universe can start expanding in that direction. Okay, that's for me, the sort of what I'd call the Big Bang.
So where's the Big Bang on that line?
Oh, I guess I'd do it here.
Just after
that.
Okay.
Yeah.
Okay, so we're reheating. So what is the catalyst for the end of inflation and the start of reheating?
Fantastic. I can draw a picture.
Okay.
Draw a picture.
Of course you can.
So, the inflation is driven by what we call the scalar field. So we'll give it the name phi. So this we call the inflaton field. This has associated with it two terms. If I was to write down the energy of the phi, it's got a derivative. It's kinetic energy, half mv squared. We learnt at school. This is the kinetic energy of the field.
What's that dot? There's important. Is that?
Yes.
That means. Okay, right.
Is d phi the rate of change of phi with respect to time?
Okay.
So velocity.
Okay.
Velocity in the field.
Okay.
Plus, and then we have its potential energy. So the energy is the kinetic energy, and then actually it's got some gradient energy. But it's this term I want to concentrate on. So a typical form for V of phi might look something like this. It would go up to some constant type thing as a function of phi. So in this region here, where for large values of phi, can you see it's very flat? You like skiing. You know, so something. You remember? Oh, you're from Australia. You wouldn't have gone sledging very much, huh?
Nah.
Okay. Imagine you're on a hill, okay, but you're on a sledge or you're on skis, and if the hill is very flat, you're not going to move very much. You might move a little bit because perhaps it's got a little bit of a slope, but unless you actively kick it or really go for it, you're not going to move. And that's what happens early on. The field stays up here. And so all this energy here, in this potential energy, is a constant. And it dominates everything. It dominates. And so this is what causes inflection, this bit. But the field is beginning to go down here. Slowly, slowly, slowly. But eventually, can you see, it begins to feel the curvature here. It begins to go a bit quicker. So now you're going down the steeper bit, but now you've realized, oh my, I'm on the black rung. This term now becomes important. All the time V is dropping because it's going down. This term becomes important. And so inflation ends, say here, when that term becomes as important as that term. It's called slow roll, breaks down, but we don't need to go there. So inflation ends. So now the universe has stopped inflating. We're here on this plot. And what this field does, it'll be symmetric, and it begins to oscillate. This field now begins to oscillate around the minimum, backwards and forwards, oscillating backwards and forwards. This is the only energy we've got. We've lost all the particles. We've lost all the radiation. This is the only energy we've got in the whole universe to play with. And what happens is this field, phi, is coupled to other fields. And as it oscillates, it begins to decay. Phi begins to decay to other fields, maybe fermion fields, which then give us, say, things like the electron, or maybe other fields like this, chi, which eventually perhaps give us the Higgs. And what happens is, as it couples, it decays, and there are two modes of decay. And I just want to tell you about them both, because one of them is familiar to you, and you have no idea why it's familiar. The one that isn't particularly familiar is called perturbative decay. That's where this field phi is only very weakly coupled to this field, very weakly. So each time it oscillates, it thinks, I can't be bothered to decay. Can't be bothered to decay. But eventually it decays, just very slowly. So it oscillates backwards and forwards. It's not a very efficient way of reheating, but it is decaying to create these, and also, of course, it can create photons, which is what you and the light that permeates here. But it's not very efficient. There's another way, which is called parametric resonance. Preheating is the technical term. And the way it works is you're familiar with. You've been on a swing. You've taken your son to a swing, I guess. And you know it. You push a swing. If you totally push a swing at random, it won't do very. It'll go up a bit and then it'll go a little judder a bit. But if you hit the resonant frequency,
magic point,
it goes woof. And after about 2 or 3 cycles, it's gone whoa, right up. And then you're a bit worried about this. So you try and stop it. For old cars, those of us who used to be in old cars, the mirror of a car would, if it hit about 45 to 55 miles an hour, it would start vibrating. Because the mirror, the natural frequency of the connecting part of the mirror onto the window exactly matched the frequency of rotation of the car at that speed. And so it would, the resonance effect would cause this to go going like crazy, and you'd lose, you couldn't see out in the back very well. That's all been sorted now, but I remember that with my dad. Well, that's what he told me anyway. So what happens then, the alternative way is this thing has what we call parametric resonance. It actually just goes woof, maybe 1 or 2 cycles, and it decays. And it decays into, so this inflaton field is decaying, and it first of all, so this is the parametric resonance. This is active areas of research. Okay. And it's that prompted me to try and mention it. So phi, it decays, and it decays into what we call condensates. It forms a condensate. And these condensates are like, because phi wants to be together, a condensate is like something that sort of wants to be a bigger entity together. And in particular, it can form a thing called oscillons. And I'm particularly like these, because I wrote one of the first papers on oscillons in 1995 with Marcelo Gleiser, my friend. We wrote a paper on oscillons, and these are fantastic objects. These are objects that have no right to exist. Okay, they form they've got finite size. They just exist on energetic grounds. There's no conserved charge. There's no winding number like you would get with a cosmic string or a monopole. They just exist on this because the energetics of them allows them. And whereas they should decay in the space of, say, 1 cycle of this field which bounces up and down, these last 1 billion cycles. And so what's of interest is these can be relevant for this effect. And so these oscillons, one of the things we're now investigating is the formation of these oscillons and how long they'd survive as the universe is reheating. And it reheats a lot more efficiently through parametric resonance because of this aspect where if you hit the right frequency, the thing decays very rapidly and you produce lots and lots of these particles, in fact, of these ones, very, very, very quickly. And that can lead to a really hot universe quite quickly, which then eventually totally reheats via the perturbative effect at the very end. But that's basically the idea of the reheating, that this inflaton field, which has led to us understanding the density perturbations, which are the fluctuations of this field leading to structures, which has allowed us to understand the initial conditions of the hot Big Bang, that it's that energy that's stored in that field that then gets converted through this oscillations into the particles that we see today that then reheat the universe, and that then takes me to this point here. And that's what I would then say is the start of the hot Big Bang.
So the inflaton field kind of shook itself to pieces.
It shakes itself to pieces.
And the debris is particles.
And this is part of the debris, the oscillons. That condensate, actually, it breaks up into these oscillons, which are smaller debris particles. form out of it.
And do the oscillons then break down into something else?
They break down into something else because they've got a finite lifetime. They then decay.
So do we go from the inflaton field direct to electrons, or do we go via the oscillons?
Good question. You don't always go via oscillons. If the coupling is too strong to these other fields, these oscillons don't. That's what we've been discovering. Okay, in the last few weeks, these oscillons don't form. I don't want to go there. No, if nature's been like that, if it's coupled these fields very strongly to these fields, then it goes directly.
Just so I'm clear, is this, you said you've been discussing this in the last few weeks amongst your fellow researchers. Does that mean what you've been telling me now is not like accepted law, or it is the accepted way that particles formed? Or is this kind of, you and your teammates have come up with this and you're hoping it becomes...
I wish I'd come up with it. The idea of reheating has been around since inflation, in that it was realized the universe is empty. So how we're going to... That's a balmy universe to live in, right? It's not our universe. So it was realized very early on that there was a possible mechanism. The details of the calculations are very difficult because they're called nonlinear equations. And you've got more than one field. You've got this field phi, but you've got these fields that they're coupled to. So your equations are long and difficult. You can't solve them analytically. So numerics play a big role. And I think the progress is that the numerical scale, the computers are getting larger. You can do bigger simulations, so you can trust your results a bit more. And I'd say that's where the field is going. I remember reading about this thing, parametric resonance, and I actually remember down in the tea room at Sussex, having the paper I was having a cup of tea back in 1994. That original paper came out by Linde, Starobinsky, and Kaufman. So the idea has been there for a long time. But what we've been able to do, which I don't think people have done, is we've been able to actually couple these together and seen properly when these form. We can see them forming in the simulations. And so we know when they're not forming and when they are forming. And we can then work out the effect of having these objects forming as the universe decays, as these fields decay and create the particles.
Is the inflaton field totally gone now then? That's no longer exists?
Yeah, the inflaton field is gone. Today is gone. There's a final bit of this process where, these oscillons are made up of the inflaton field. So as they fragment, there's still a bit of residual inflaton field, and that's the bit that then decays via this perturbative effect I was talking about.
Okay.
Are we reading the universe?
So we went from inflation.
Yeah.
Then the inflaton field shook itself to pieces, and somehow we got all these particles. Yeah. And then the particles all went bang and scattered via the Big Bang.
So they went bang. So that's the.
But they were distributed by the bang.
Yeah. Well, it's not a bang in that's not a singularity there. That's not a space-time singularity. So this is a smooth effect that's going on here. But I would argue that this is what we would normally call the hot Big Bang, in the sense of it's a universe that's got all this radiation and matter in there and is expanding out. That's what I would call the hot Big Bang. But it's an unfortunate term at the level of when it was first introduced. We had no idea about inflation. We had no idea about reheating. That there, the Big Bang really was that you'd say the universe began from this singularity somehow or close to it.
The old-fashioned Big Bang that everyone thinks of as being there's nothing and then suddenly there's something. Yeah. That's not the hot Big Bang. That's the start of inflation.
I would argue that's the start of inflation. And so the same issue's still there, right? How did that begin? That's still there.
What's that? Is that a cold Big Bang?
The hot here is referring to the fact you've got all this radiation that's been produced, and that's got temperature.
What do people in your field call the point where inflation starts again?
Start of inflation.
Start of inflation. Okay, right. Yeah. And that's what I thought the Big Bang was, going from zero to something.
Yeah. And in fact, you would think of the start of inflation, which I've put here.
On the right, yeah.
On the right. It could have been anywhere along here. That the main contributors to the energy of the universe is this field. And I wouldn't be thinking of this necessarily as a particularly hot environment. It could be, but this has to be dominating for this to take place. If there are other contributors to this, let's say this is the energy of the whole universe, if there are other terms coming in here from radiation and particles and they're dominating, this will never inflate. You need this to be constant and to be dominating for inflation to occur. So it's a good question. Would I call it a hot Big Bang? I wouldn't probably call it a hot Big Bang. Yeah, maybe we should introduce the cold Big Bang.
You need a better word for the start of inflation, but I don't know. All right, I'll leave that with you.
Okay.
All right. Professor Copeland and his collaborators have a new paper out on this topic, just recently uploaded. I'll put a link in the video description. Also in the description, I'll put a link to the University of Nottingham's School of Physics. Find out more about their research and also opportunities to work or study there. If you'd like to see more 60 Symbols videos, well, of course I'm going to link to those too, including some really good ones with Professor Copeland. Some deep dives on the sofa. Check them out.
It emerges as this smooth, homogeneous, isotropic region, which is what we now see.